Welcome to another episode of Complete Developer Podcast, the podcast by coders for coders about all aspects of creating your best life as a developer.
I'm Will, the accomplished developer and aspiring software architect.
And I'm Beej, the journeyman developer sharing my journey in development.
This episode was sponsored by the PVS Studio team. It promotes static code analysis methodology in general and its PVS Studio tools in particular. Static code analyzers allow you to find bugs in source code at the development stage. This helps to reduce the price of fixing them.
PVS Studio performs code analysis and issues warnings on the fragments of code with a high probability of having bugs and potential vulnerabilities in them. The tool supports C, C++, C#, and Java, and it can work with Visual C++, GCC, Clang compilers, and some of those used for embedded systems. The analyzer works on Windows, Linux, and Mac OS. PVS Studio can both be used as a standalone tool and integrated with Visual Studio, IntelliJ IDEA, SonarQube, and so forth.
In the show notes, you can find links to the PVS Studio website and the article Technologies Used in the PVS Studio Code Analyzer for Finding Bugs and Potential Vulnerabilities.
Where mathematics and philosophy meet, you'll find formal logic. It's a systematic study of valid inference. In it, one starts with a proposition or assumed hypothesis and derives a conclusion. In this episode, we'll look at the basics of formal logic, starting off with some definitions, and then we'll get into the rules governing logical inferences. But before we get started, Will, what have you been fighting this week?
Well, I spoke at Nashville Software School and at Free Code Camp. So Free Code Camp was this past Saturday, and there was probably a half dozen to a dozen people from Nashville Software School cohort 33 who I then spoke to last night over there. I actually signed one of my books for the first time, which is a very surreal feeling. So yeah, that was pretty cool. I also have a brand new keyboard tray designed specifically for the Microsoft Natural Keyboard.
Nice.
Yeah, because all the others were either too short or the key tabs would go off the back, and so you had problems with that. And the only problem is now I'm having some trouble with the arrangement of my desks. So I had to pull my monitors closer, and then that meant that I had to kind of move the microphone a little bit, which now means it doesn't quite reach my face. So it's all weird. I'm going to have to completely redo my desk, get different wires and just do a bunch of crap to it, which is going to be annoying. It's probably take 3 or 4 hours. Might see if I can make my daughter help me with it because she's probably listening to the podcast anyway, so it'll annoy her. So thinking that that's coming. I got a book chapter of my next book done, got another one edited, and I'm writing another one now, and another one hit Simple Programmer site.
Oh, wow.
I think, or maybe one of those three. It's kind of like the podcasting thing where you time travel. When you talk about, okay, well, this thing came out, but I haven't looked at that in weeks, man. And I got a little bit behind there for a bit because I had one chapter that was 15 pages. And then the next chapter was 25 pages. And then the next one was 15. And, they should have been 8 to 10 pages probably each for most of the stuff. But to cover everything, they were long. And so that meant that editing was slow and everything. And so I just had to scramble to catch up. And yesterday morning, I got up at 5:30 in the morning and I was doing, regular work, writing, all this other stuff. And I finally went to bed at 10:30 at night. And I did not get to have much of a break at all. I think my only break was going to the Mexican restaurant for lunch. So that was a little brutal. In other news, I was using my Russian flashcard app and I noticed a translation error and I actually picked up on it and reported it.
Oh, that is really cool.
Yeah. It's just on the first shot. I was like, this is wrong. That's it.
That is really awesome.
I copied my Russian teacher. She's like, yeah, you were right. I'm sure she's like, why are you sending this to me?
That is really cool.
So how about you?
Well, I met my girlfriend's parents Sunday. Yes, I admitted it. I have a girlfriend. Hi, Amanda. And I realize now that you can't see me waving at you, so I will stop.
Yeah, it was kind of weird. I could see it.
Yeah. So that was interesting. Went over after church, had lunch with her parents. Her dad grilled steak. He did a really good job. Got mine like right at rare to medium rare. Really good steak. Then we went and saw Overcomer. It was a movie.
Okay, I'm not familiar with that one.
Yeah, it's not super mainstream. Like it's in theaters, but it's a Christian movie. So interesting. I have a test tomorrow in my discrete class. I've been studying for it all week.
I do not miss those days.
We've also had quizzes every day in class because we were a little bit behind and the professor wanted to catch up for the test. So it's been a bit of a rough week. I was supposed to have yesterday as sort of a catch up day in class and like answer questions and stuff. And then like Monday was supposed to be the last of the new material, but that wasn't the case. I had homework and 2 quizzes on Monday and then a quiz yesterday and homework. It's been insane preparing for this. Like that's all I've done the last week is just not just studying for the test, but also all the other stuff for the class that has been piled on at the like we got to get all this in for the test.
Yeah, I remember those days, man. Ugh. There's just no way to teach that class without it being awful, I think.
Mhm. I really love the layout of the class. It's great. She has videos of the lecture for us to watch, which makes sense because
That would have helped me a lot.
yeah, you can go back and you can rewatch it, and it's basically her working out problems and then talking about it and listing stuff out. It's really good. Then you've got the book, and each lecture or each section that we have homework from it due at the beginning of class, and then there's a quiz on it at the end. So what she does is we'll come into class, and instead of lecturing, she'll go over the homework or the previous quiz, depending on sort of where people are. But she'll go over the homework and then go through a practice quiz and answer questions and stuff like that. So you've already seen the material like 3 times before you actually take the quiz.
Nice.
And the homework's only worth like 2 points. The quizzes are like 10 points. It's not a huge thing, but it's kind of nice because I'm getting it. And so by the time it hits the quiz, I think the only questions I've really missed were around things like me misreading the question or something. So that's pretty cool.
Yeah, that's good.
Needless to say, this episode comes almost directly from studying for my test. For a little bit more on how computer science affects our lives, let's go ahead and get into book club. So we are continuing on Algorithms to Live By, The Computer Science of Human Decisions by Brian Christian and Tom Griffiths. Each chapter in this book looks at a different algorithm or problem that algorithms are designed to solve. Chapter 1 looks at optimal stopping. In it, the authors discuss the secretary problem, or how to know when to stop looking for a new secretary, with the limitation that once you've interviewed a secretary, you have to either make a choice to hire or you cannot review them again.
Yeah, I like that chapter in that book, by the way, because it was basically here's how you break down the cost fallacy versus the fear of missing out and mathematically solve that.
Yeah.
And that was just really, really interesting to read through that.
I like how they also apply it to areas of our lives, such as looking for a new apartment or dating.
Yeah.
And on that, chapter 2 goes into kind of the explore exploit problem. Chapter 3, I really enjoyed because it got into sorting. And that's, I think when I was in high school, learning sorting algorithms is when computer science really started to kick in for me. And I really felt like I understood what was going on. And that's weird, I know, but that's just, for me, that's when it was. But they spend some time talking about big O notation and also how sorting doesn't always improve searching and looking at what's the actual end goal here with the sort. So it's really neat and really cool. I have a link to it in the show notes. Who's talking to us this week?
Well, we got an email from Katie Hagen Coleman saying, "Hey guys, just dropping a quick line to let you know I always enjoy listening. I repeatedly have that feeling you get when you're in church for the first time in years and you feel like the preacher talking directly to you. Like, how did you know I was struggling with that? Anywho, keep doing what you do."
Katie, I go to church all the time and I still get that feeling pretty much all the time. Sometimes the preacher even calls me out by name for being a computer programmer. Well, okay, that was only once, but it was really cool when it happened.
Yeah, I think that's in the Ten Commandments somewhere. Thou shalt
Yeah.
not do the binary. Pretty sure it's in there.
He was making a reference and he said, and if you're a computer programmer like BJ, and I was like, he called me out. That is so cool.
It's probably the first time you've been called out in church that it's helpful.
That's probably true. But Katie, send us another email with your contact information to waterbottle@completedeveloperpodcast.com. Guys, if you'd like your very own Complete Developer water bottle, leave us a review in iTunes or comment on the website or any of our social media. We post all of our episodes to Twitter, Facebook, and LinkedIn. We're also on Instagram and Tumblr. And if you've been following our Instagram account, I've been posting on there since I've been going to different conferences. Actually got to meet the guys from Coding Blocks last weekend.
Yeah, I'm jealous on that one.
So much other stuff has gone on that I didn't even mention that in my update. But yeah, I got to meet all three of the guys from Coding Blocks and hang out with them down at Atlanta Code Camp. It was really cool. So when you were speaking there, I was speaking down in Atlanta. That was awesome. You guys could join the conversation anytime via Slack by going to slack.completedevelopernetwork.com.
Formal logic is the study of statements or propositions and deductive arguments. It removes the confusion of language to focus on the application of reason. To do this, formal logic abstracts the content and replaces it with a symbolic notation.
Formal logic is a priori, meaning that it does not rely on observations for data. In this regard, it's more analogous to mathematics than other sciences. The process of reasoning or the psychology of reasoning are separate from formal logic. It is also different from the art of correct reasoning, since that is the application of logical principles to particular cases. Formal logic serves as the foundation for organized reasoning, such as scientific studies or criminal investigations. Circuit logic, the logic of computers, is a direct analog of formal logic.
In this episode, we're going to discuss some definitions and basic concepts of formal logic. Most of this was taken from BJ's study of discrete structures this semester and his textbook, Mathematical Structures for Computer Science.
Which is really a good textbook. I have picked up a lot from it. It's a good foundation, and then I get a lot from working the problems and watching my professor work the problems.
Yeah, I think that may have been part of my problem in that class too, is I had so much other stuff on my plate that I couldn't stay ahead of the class.
Mm-hmm.
I think if I'd been able to work through stuff and then come in with questions versus, okay, this is brand new and you're catching up to the lesson, that probably would have helped a lot. But I mean, I had one Bible class that was probably harder to study for than calculus was.
I remember those.
Yeah, that one professor that like was basically there when the whole thing was written because he was like, he was older than Yoda. I mean, like, you go up there and you like look at his Bible and it's all in Greek and you're just like, wow, okay. You know exactly who I'm talking about.
Yep, I know exactly who you're talking about. Yeah. Anyway, I talked about it earlier, but the structure of this class is great because it has you looking at the material at least 2 times. At minimum, 1 time if all you do is the homework and you don't even read through it. But like I get it 3 times before I walk into the class because I get it from reading the chapter, watching the video, and then doing the homework. It's really good. So we're going to go ahead and jump on in to some definitions. A statement or proposition is a sentence with a truth value.
Yeah, in other words, that means that it can either be true or false. So if somebody says some apples are red, that's a statement because it can be verified as true or false, provided that you have a discrete way of denoting red. I've hung out with a few too many philosophy majors. It's like, but
yeah.
Whereas if you say something like blue is the best color, that's not a statement because it's an opinion.
Mm-hmm. Here's the thing. The sky is falling is a statement because it can be proven true or false. Or grass is purple is a statement because it can be proven true or false.
Right. And you could even say the sky is falling because of gravitational attraction of all the atoms up there that matter. But it's really interesting when you get into this stuff, like the things that you think are provable versus what is provable. Mm-hmm. And that's one of the really tough things you deal with in computer science at a deep level is, hey, this is not a falsifiable statement, so it's not really provable either.
I think on one of our quizzes, our professor had a list of sentences And she said to select which ones were statements. And one of them was UT orange is an ugly color.
Well,
And while my personal opinion was to say, yes, that is true, and therefore a statement, since it is in reality an opinion, it could not be a statement.
right. But then you could prepend something and say, Beej thinks UT orange is an ugly color. And then it becomes a statement.
Then it becomes a statement because there is a truth value to it. It's
Right.
truthy or falsy if you're a JavaScript developer.
Oh, no. You had to go there.
Yes, I did.
Yeah, good old JavaScript.
Statements are represented by capital letters such as A, B, or C.
These could represent literal statements such as in a language, or they could represent mathematical statements that can be proven true or false.
The whole concept here is that they can be proven true or false. So some apples are red might be represented by the letter A. 2 plus 2 equals 4 might be represented by the letter B. And so you would say some apples are red and 2 plus 2 equals 4. Therefore, Will wears glasses.
Yeah, that's not a valid follow through. But the idea here is that you're assigning these things to variables. You're putting abstraction around it.
Yeah. So these are the basis for logical comparisons. Formal logic compares the truth values of statements to each other. What the statement actually says is completely irrelevant in the logic. So whether it says some apples are red, Will wears glasses, BJ is holding a rubber duck.
Which he probably is anyway.
I actually am.
Of course you are.
The thing is, it's the truth or Boolean value that is of value in formal logic. And that sounded confusing, but it's going to only get more confusing. Basically, it doesn't matter what the statement says. It matters that it can be proven true or false.
Right. And then you can assign a value to it, and then you can do math on that value.
Right.
So logical connectives are used to compare the truth values of statements. Logical conjunction compares truth values using Boolean and. So in other words, it's a conjunction of those two statements.
Mm-hmm. So for a conjunction of two statements A, B to be true, both A and B have to be true. The statements A and B are called conjuncts here, and it's symbolized as a triangle with the base removed.
Right.
So it's hard to describe this.
It looks like the carrot character with space in between the 2 points. Yeah. You just got to kind of look at it. I don't know of a good way to do it.
Yeah.
I can't come up with anything to explain it. You just got to look at it like two sticks pointing at each other.
Yeah. Like I said, it's like a triangle with the bottom side removed.
Yeah.
Where the point is up.
And so the next one is a logical disjunction, which is the same as a Boolean or.
Mm-hmm.
So for a disjunction of A and B to be true, either A or B must be true. Now, they both could be, or just one of them.
Yeah. The statements A and B are called disjuncts, which is not to be confused with adjuncts.
Right, which are the underpaid professors. Right.
Right.
Got it.
You got the joke I was going for, yeah. And this one is symbolized as an inverted triangle with the base removed. So it's basically the conjunction, the and symbol, upside down, where the point's pointing down and the top side of the triangle is removed. So the way I think about this is, so if A and B were at the end of those two lines that aren't touching, and I reach down to pick it up, I would pick up the top of the triangle and I'd pick up both A and B. But with the or, they're sitting on top of it and then coming together. So if I reach down, I would pick up A or I'd pick up B. It's the way my brain works, man. I don't know, but it's how I remember it, and it's how
that is a very interesting spatial mnemonic. I don't think I would use that one, but okay, whatever floats your boat.
It has gotten me through several quizzes and tests. So.
Yeah, if it works, it works. I've got stupid ways I remember stuff too.
Statements combined to say if A, then B are logical implications. They basically read as A implies B.
And logical implications are symbolized by an arrow pointing from A to B.
In them, the truth of A leads to the truth of B. If A is true and B is true, then the implication is true. If A is true and B is false, the implication is false. However, a tricky one is if A is ever false, then it doesn't matter the value of B. It's like arguing with someone that says the sky is green.
Yeah.
Whatever they say is just going to be true because you're like, whatever, man.
Well, it's just more like they don't have a truth value and it's already short circuited
Yeah.
at that point. So you can't infer anything off of it because it's like a dead circuit.
Yeah. It's basically, there's no point in arguing with someone who starts from a false preposition. So you just say, whatever, man, you're right, and go on.
Right. Because that's how you win political debates. If we want people to start with the false, yeah. So equivalence in this case is not really connective, but it's a shortcut for a more complicated set of connectives.
Basically represents A implies B and B implies A.
Right.
So they imply each other. Therefore, those two statements are equivalent. And it's true only when A and B have the same truth value.
Right. So true implies true. Or if the expression could be reduced to true on both sides, then they're equivalent.
Yeah.
So it's very much like algebra. Like if you want to think about it that way, that's kind of the sort of thing we're going for here, except it's logic instead of arithmetic.
Equivalence was the one that was the hardest for me to wrap my brain around. I had to do quite a few problems with it and then walk through it in class. And I really still didn't get it until I started writing this stuff down for this outline.
Yeah.
It's funny how I use this as studying. And it's funny how that is because I really started to pick up on it. And I'm like trying to figure out how would I explain this is when it started to click. So it's really complicated, but it's basically that when A equates to B, it's saying that A implies B and B implies A. So you can do a truth table on that. Now, a unary or singular connection commonly used is negation. And what that does is return the opposite of the Boolean value. So it's symbolized as, it's called a naught, but either like a tick or a single quotation mark.
Right.
With like a single quotation mark or B single quotation mark. And if you look in the show notes, all this stuff will be written out so you can easily see it. Hey, this is a great way to get people to check out our show notes and leave us a comment. So,
yeah.
Remember, that's the way you get a water bottle.
Right. So if you submit a comment, then you're in the running to get a water bottle.
Right.
That's how that statement would go.
That is.
Truth tables represent all possible Boolean values of statements, such as and or.
So in a truth table, each column of the table represents a statement or a connective. What I usually do, and I think this is the simplest way to do it, is to start with your statements. So if you have A and B or A, B, and C, you start with the basic statements. And then if you have more complex connectives, break them down into simpler ones.
Right.
So if it's like A or B and C implies C and B, then you would break it down to A and B and C, break those down so that it's easier to plug the pieces in where you combine those simpler connectives.
It's almost like, do you remember in high school biology where you had to do Punnett squares for genetics? And it's a very simplified version of genetics too, by the way. It's like that. It's very similar in structure to that as far as how you break things down and how you break out the statements. It's just those statements are genetics versus logic statements.
And let's just use a simple example throughout describing a truth table. So we're going to use A and B.
Okay.
So your columns would be a column for A, a column for B, and then a column for A and B.
Right.
Each row on that table represents a set of Boolean values for each statement and the resulting comparison. So first off, to compare two statements, you're going to kind of want the following Boolean values. So you'll have like true, 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 false, false, true, false, false. A is true, B is true, A is true, B is false, A is false, B is true, A is false, B is false.
Yeah.
Then once you have those, compare the values using the connectives for the third column. So you go for the first one, true and true is true. True and false is false. False and true is false. False and false is false. You're going to have 2 raised to the power of n number of rows, where n is the number of statements. So because we had A and B, we had 2 statements in that truth table. We had 2 to the power of n, 2 to the power of 2, 4 rows. It basically grows exponentially as the number of statements increases. And what my professor suggested to do so that you get all possible combinations is to go, all right, I'm going to start with half.
Yep.
So the first statement, half true, half false, and then fourths, and then eighths, and then sixteenths. And eventually you get down to where it's true, false, true, false, true, false.
Or you miscounted and you start over.
Yeah.
Yeah. Because that happened to me a lot.
Yeah. It's fun, complicated, and interesting.
Yeah. So, given all of this, obviously you're going to have an exponential growth that's going to occur. So, like, if you just got 2 statements, you're going to have a truth table with 4 rows. And this does get pretty complex, especially when you go to the next thing, which is statements, connectives, and parentheses, because now you're starting to combine larger, more complex statements. So if you think about like how we were talking about a really small one and how long that took, now think about like a full-on logic problem that's, got maybe 5 or 6 variables and a whole bunch of stuff going in and out. Think about how big that truth table gets.
Yeah. These can be strung together to create expressions. So expressions that are legitimate strings are called well-formed formula, or WFF. Basically, this applies the rules of syntax or sentence structure to expressions. So in kind of a funny way, formal logic is like the grammar.
Yeah, it is. It makes me think of when I started getting my head around abstract syntax trees a lot, because it's like you have the abstract syntax tree, right? That's your columns effectively. And then your rows are the crap that's going into that. And then the output of it is what the result is.
Yeah. The thing with them is they can be statements or they can be expressions of statements and connectives. And the WFFs, well-formed formulas, have their own truth value and can themselves be used as statements.
Right. So, like, if you know that it always comes out true, for instance,
Yeah.
then you could just reduce it to true. Or, you can almost do like a memoization of it type thing.
Yeah.
Yeah. And this is kind of hard to explain just in audio. But again, if you hit the show notes, that will help you out a lot. Now, there is an order of operations that has to be discussed anytime we talk about this kind of stuff, because I've noticed on Facebook, like, people will put math problems up there, and like 90% of the people I know will get them wrong because they don't know the order of operations from math. And it just completely blows my mind.
Yeah. I feel you.
I just twitch when I see it. I'm like, why are you doing that?
I stopped even looking at those because sometimes they'll put them in there that are just like really.
You ever tried to like reverse engineering how they got that answer?
Yeah.
That's fun.
Because
sometimes you look at it and you're like, I can't even break the rules in a way that makes this happen.
So if you guys remember from middle school algebra, PEMDAS, or pre-middle school.
Right.
I don't remember how old I was when I learned that. 6th grade, maybe?
I think I learned that between 4th and 5th at like Young Scholars or something.
It might have been before 6th grade. I don't remember exactly. But so with this, as with everything, you start with the parentheses. The innermost parentheses first.
Right. You can think of parentheses as just, here's how I override the order of operations for everything else.
Right.
It's like exclamation important in CSS.
And then the next thing you do is your negation, which I would equate that to exponents.
Yeah.
And then you have, it's basically a -1 exponent. If you think about it. But then you have conjunction, your and. And if you guys remember from our episode on Boolean logic, and is basically multiplication.
Right. And then you have disjunction, which is your or, which is addition/subtraction.
So let me just say something real quick for remembering the difference to this, because I had one of my classmates say he always got confused with that. I said, the way I remember it is I just take 2 opposite values, which there's only 2 possible values, 1 and 0. And if I multiply 1 and 0, I get 0. So that is like an and. If you and true and false, you get false. But if I add 1 and 0, I get 1. So that's like an or, because if you do true or false, then it's true. And that's how I remember the order, that conjunction or and comes before disjunction or or.
Yeah. And then following that, you have implication. This is where the thing kind of starts breaking down a little bit.
Yeah, at this point, we've reached the end of PEMDAS. We've done PEMDAS. Now it's just implication, and then you have equivalence.
Right.
You would do the other things first, and then you would do the implication or the equivalence. Next, a tautology is a WFF or well-formed formula that is intrinsically true no matter the Boolean values of the statements.
So like A is A.
Yeah. Or the simplest example that I can think of this is A or not A. It's always going to be true. No matter what the value of A or not A will always be true.
Yeah, I mean, bear in mind this is, formal logic and provable statements.
Yes. A contradiction, on the other hand, is the opposite of a tautology. It's something that's always false.
So that's A and not A.
Yeah, which will always be false no matter what the value of A is. Now, one of the most well-known tautologies, and we talked about this in the Boolean logic episode, is De Morgan's law. And it states that if you take the negation of A or B, it's the same as negative A or not A and not B.
Right.
So you can split that negation to the individual statements, but then you change the connective.
Right. And this is really handy like in circuit design sometimes because you might be able to flip the way that that's expressed to simplify the circuit, for instance.
I remember in a class I had last year, I don't know if it was first or second semester, we basically had to build an entire circuit with NOR gates.
Yeah.
Or NAND gates. It was just, all right, this is all you've got. You've got to build a circuit that does all these different things with just this.
Yeah. It's a really good exercise.
Yeah, it is. It's interesting for sure. So now we're going to get into talking about some rules that you can apply to logic statements. Equivalence rules state that certain pairs of WFFs are equivalent or return the same truth value for a given input. The first of these is the commutative rule, and that states that the order of statements does not matter when conjoining or disjoining two values. So basically, A and B is the same as B and A. So right now, Will is wearing glasses and Will is wearing headphones. It's the same thing as saying right now, Will is wearing headphones and Will is wearing glasses.
Right. I mean, it's like, addition, for instance, is commutative, right? Mm-hmm. And multiplication is the same way.
Yeah.
Whereas division, not so much.
Yeah, that's true. That's true. It also applies to disjoining. So A or B is the same as B or A.
Right.
So Will is drinking beer or whiskey is the same thing as saying Will is drinking whiskey or beer.
Right. Because he has no fear. How about that?
You go, man. You go. I got nothing for you.
No, I would have had whiskey if I'd realized that this was going to be the outline. Have beer.
Fair enough.
So the associative rule states that when conjoining or disjoining three or more statements, the order does not matter.
So you could say A and B and C is the same as A and B and C.
Right. And where B and C is in parentheses implicitly.
Yeah. You could tell that in my tone.
Yeah, totally.
Yeah, you can hear the air quotes.
Right.
You can hear the air quotes.
Totally.
The same applies to or. A or B or C is the same as A or B or C. So let's just go back to Will because I'm looking at him on the screen here. Will is wearing glasses and headphones, and he has a microphone in front of him, is the same as saying Will is wearing headphones and he's wearing glasses and has a microphone in front of him.
Right. So now let's go to the next one, which is De Morgan's law. And that states that the negation of the conjunction or disjunction is the same as negating the statements and applying the opposite connective. So let's take that gibberish and we'll turn it into something you can actually understand, because that sounds pretty awful just from reading it.
Conjunction, junction,
I
what's
knew
your
that was gonna come
function?
Conjunction, junction, what's your dysfunction? What? Okay, so not A and B is the same as not A or not B.
So saying Will is wearing a fedora and a mini skirt, not, is the same as saying Will is not wearing a fedora or Will is not wearing a mini skirt. I don't know. I just picked two random things.
I was like, which Linux conference did you go to? Oh, wow. You got me confused for somebody.
Oh, I should have said a fedora or a red hat. That would have been a lot funnier. Well,
That
no, I
would've.
think a mini skirt was funnier. Let's do that. So also you could say Will is not wearing a fedora or red hat is the same as saying Will is not wearing a fedora and Will is not wearing a red hat.
Right.
And that just sounds really confusing. Guys, look at the show notes because
It makes a little bit more sense when you can hear it and you can see it.
yeah. What I do want to point out is that the conjunction becomes a disjunction and vice versa. Basically, and becomes or when you do this, or becomes and. It flips.
Right. And I'd like to point out that I'm not wearing a fedora, a red hat, or a mini skirt, much less and. Just want to clear that up for everybody out there, since I had to be the butt of the joke, but hopefully that'll help you remember. So the next one, the definition of equivalence is also an equivalence rule. And this was stated earlier as a shortcut for connectives.
In reality, it is an equivalence rule, or more directly, it's basically the definition of equivalence. So, where we said that if something is equivalent, it means that expression, the A implies B and B implies A, is basically an equivalence rule.
Right.
The next set of rules we're going to talk about are inference rules. And these state that if you have certain WFFs and or statements, that you can derive others from them.
Right. And so the first one, of course, is modus ponens, which is actually not a Roman general. But it states that if you know a statement and know that the statement implies another statement, then you can derive the second statement.
Yeah. So if you know A and you know A implies B, you can figure out B from that.
Right.
And you can prove this using a truth table. So the next one is modus tollens, which is actually a Roman toll guard.
Right. I think it's a Harry Potter character. Seems like that's
it's a Harry Potter curse. You just see someone waving a wand, modus tollens.
Right, exactly.
You snap on the L.
He's in Azkaban for jaywalking. He's just not even a really good villain. Now that we've helped you remember this with really, really bad references. So this basically says if A implies B, then not B gives you not A.
Yeah. So if you know what A implies B is and you know what not B is, you can figure out what not A is. And you can use these in logical proofs, which is on my test, but we're not getting into in this episode because just going through this stuff took up, most of the episode.
Yeah.
We may have another episode on logical proofs. Still got a lot more left in this semester, so I'm sure I'm going to get more.
It just gets worse, just so you know.
I've looked through the book, I know. I'm looking forward to it. I actually really enjoy it. I am learning a lot from this class, but yeah.
There's a word for that. It's called masochism.
So the conjunction rule states that if you know two statements, you know their conjunction. So if you know what A is and you know what B is, then you can know the conjunction of A and B. And you can obviously create a truth table to prove this.
Now, simplification states that if you have a conjunction, you can get the statements. So, for instance, A and B gives you A and B. Not, that latter one not being the conjunction. It's kind of hard to, because we also use the same words in English.
Yeah. So a good way to say it would be if you know the conjunction A and B, you can derive both A and you can derive B.
Right.
This makes sense if they're true, but I'm not sure how it works if they're false because A or B could be false. Basically, if A and B are true, then we know that both A and B are true. But if the conjunction A and B is false, A could be true and B could be false. A could be false and B could be true.
Right. It's not provable without additional data.
Yeah. So it only works if it's true.
Right. Addition states that if you know a statement, then you can infer its disjunction with another statement. So, for instance, A would give you A or B. So, if you know that A is true, then you can figure out that A or B is also going to be true.
Yeah. And again, this only works if A is true.
Right.
Doesn't really work so much if it's false because B could be anything. Well, anything Boolean. So it's either going to be true or false. But within the realm of Boolean, two options is anything.
Okay.
I think I broke Will's brain with that one.
No, you didn't break it. It's just kind of this is heady stuff, and like I'm looking at the next section trying to figure out how I'm going to explain this. I mean, it's sort of like going to the ER with a weird injury.
Mm-hmm.
Boolean logic is a lot like that. It's like, okay, how did we get here?
Yep. It's base 2 math, man.
Yeah. So propositional logic is the use of propositions or statements along with formal logic to reach a conclusion.
The propositions are also called hypotheses, and they're composed of statements which could be a simple statement or the product of a previous comparison. And when inferring a conclusion, the hypotheses are assumed to be known.
The propositions lead to a conclusion based on their Boolean values. So you would use like a truth table to show all possible combinations of propositions, and then from there infer the conclusion based on the truth values of the table.
And this can be represented as a series of propositions conjoined that imply a conclusion. So P sub 1 and P sub 2 and P sub 3 and so forth to P sub n implies Q, where each P is a different proposition, and that proposition could be a statement or a well formed formula expression. Or it could be the product of a previous statement and expression. It could be a lot of different things there.
This is called a proof sequence where the P's are WFFs or results of logic applied to earlier WFFs.
Now, assuming the Boolean values for the WFFs in the P's, then you determine when the Q is true.
Right. So I'm trying to think of a good way to explain this. It's a little bit tricky. I don't have a good way to lay this out without people looking at the show notes. Like it makes a lot more sense when you just go, okay, I'm just conjoining statements and getting a result.
So here's a good way to put this. Will has proposition 1, beer or whiskey, and proposition 2, Will has headphones and a microphone, and proposition 3, Will is on my screen. Therefore, my conclusion is we are recording a podcast.
Right. Because otherwise that conjunction of things probably doesn't happen.
Right.
Or doesn't happen. I can't think of a time it has, actually.
Not in recent memory, at least.
Yeah. Which is pretty much universal truth, right? Recent memory is the only thing that matters.
Pretty much. So, guys, this is just an overview or maybe a refresher for some like Will of the topics of formal logic. It has a lot of direct applications to computer science and programming. One that we mentioned a lot is Boolean logic, which we've had an entire episode on. You can go back and look at that. A lot of times, developers not only have to reason through confusing data, but they have to write code that tells the computer how to draw conclusions from data that's input by users.
Yeah, or you have to simplify it.
Yeah. For more in-depth details, you can check out the book that we mentioned at the beginning of the episode, the textbook I'm using for class, or you can go online and Google formal logic, and you'll get a lot of really great information. That pretty much wraps us up before we close everything out. Will, what do you have for us this week for Tricks of the Trade?
Well, I had somebody ask how I stuck around in programming as long as I have, right? Because I've been doing this for a little over 20 years since the first time I got paid. And a lot of the people that were starting or were doing it when I started are not in the industry anymore for various reasons, including a whole lot of retirements, right? Like, because you still had like the old, back then you had the old VAX administrators and all those folks, and, they're retired now for the most part. And I got to thinking about it. And I think what it really is I realized pretty early on that there's a difference between what programming is and what programming does. So what programming is typing stuff in and you get a result, right? You make the machine do something. But what it does is a little bit more interesting. We made a joke about Harry Potter earlier in the episode, and that was actually an intentional drop, by the way. And the reason I did that is, have you ever considered just how wondrous the stuff that you're doing is, right? Like right now, I can do something on my computer and I can command dead matter halfway across the planet to do something on my behalf. That is pretty wondrous. Like 500 years ago, if you told somebody I can do that, if you didn't get burned at the stake, they'd be pretty impressed. Even if you told them 50 years ago that you could do that, it's still an age of wonder. And I think that's probably how I've hung on, because that hasn't really left me. The fact that I can send a payload to a server somewhere and I can get all kinds of data that I need for a process, or I need to make money or to spend money or whatever, like that all happens transparently. And I think if you can recapture that childlike wonder, it will make sense to you how you can stay in this industry, because it's not about what programming is, it's about what it does. And if you can just hang on to that, I think you'll last longer in this industry. I just thought that was kind of profound and I wanted to share that. And that's all I got.
Stand by for Titanfall.
If you have a question or comment, please email us at neckbeards@CompleteDeveloperPodcast.com. Our theme music is an excerpt from Stand By for Titanfall by Pure Bells, available on SoundCloud and licensed through Creative Commons.
The intro music for IoTs is Hillbilly Hip Hop by Jason Belcher. For references, show notes, and to sign up for weekly emails with extra tips and insights, be sure to check out the website at CompleteDeveloperPodcast.com. You can also follow us on Twitter at CompleteDevPod and like our page on Facebook to keep up with news about the show. Catch us each week as we broadcast live, talking about what's going on in the tech world and answering listener questions.
Learn more about all of our shows and groups by going to CompleteDeveloperNetwork.com, where you'll find links to Junior Developer Toolbox, Developer Launchpad, and our other communities. Thanks for listening. See you next time.